Hello everybody, I hope you are enjoying virtual approx. My name is Grzegorz Gutowski and I will be giving a talk on online coloring of short intervals. This is joint work with colleagues from Warsaw University of Technology, Asia Chybowska-Sokół and Kostek Jodosz-Szaniawski, and my friends from Jagiellonian University in Krakow, Patryk Mikos and Adam Polak. Our paper investigates a variant of a classic problem on online coloring of intervals. In our variant, all the intervals on input need to be short, so the length of the interval is bounded, and we provide some new algorithm for this setting and a series of new lower bounds. Before I can introduce our problem, we need to define some basic notions. So this is a set of intervals, and we draw them like this, but we think of them as intervals on a real line. So we will say that these two intervals intersect, because if we would squash all the intervals on one line, then these two intervals would really intersect. So these two intervals also intersect. And we are interested in colorings of intervals such that any two intersecting intervals get different colors. So this is the same as constructing intersection graph of such a system. So we construct a graph where we give a vertex for each interval, and we put an edge between two vertices if the corresponding intervals intersect. And we are interested in proper colorings of this graph. So the first observation that I want to make is that interval graphs are perfect, and there is a very easy algorithm that constructs an optimal coloring. So basically any greedy coloring works. So let's sort the intervals by their left endpoints. So this is the first interval, and we will assign colors to intervals in that order. And for each interval, we just assign the first possible color. So we assign color red to this one. This is the next one. We can't use color red, so we use green. This next one, we can't use red and we can't use green, so we use blue. For this one, we can use red because this interval does not intersect any other interval color red. For this one, we can use blue, and for this one, we can use red, and this way we construct a coloring using three colors. And you can easily prove that such a procedure always constructs an optimal coloring. Now we want to move this problem to online setting. So an online algorithm does not have access to the whole input, and we will get information about intervals one by one. So say in the first round of this algorithm, we get information about this interval and we need to assign color to it. So we just color it red because there is nothing else we can really do. In the second round, we get information about this interval here, and well, a first-bit algorithm would color it red, and well, there's really no point of coloring it differently because what we see now are just two intervals that do not intersect, so it's a good idea to color them with the same color. What happens next is this interval is presented to us, and now we can't use color red, so we'll use color blue. And what happens next is this interval here, and for this interval we can't use color red, we can't use color blue, so we color it green. And for the next interval we can't use color red, we can't use color blue, and can't use color green, so we need to use a new fourth color. It will be yellow. And at this point we used four colors for a set of intervals that can be colored using three colors, as we did in the previous slide. And if you analyze what happened, when we colored this second interval red, we kind of failed. There's no way of extending this coloring to a coloring of all the intervals with three colors. But at that point, we didn't know that it's a bad decision. Alright, so online coloring might be more difficult, or at least first fit algorithm is failing, and it's using too many colors, but in fact one can see that any algorithm must use too many colors. Okay, so we can finish the game, and this is the last interval, and we can safely use color green here. Okay, so to analyze what happened, or to say if a coloring algorithm is a good algorithm in online setting, we introduced this measure, competitive ratio of an algorithm is a ratio of the number of colors used by algorithm on a particular instance divided by the optimum, the chromatic number of the presented interval graph. And we are interested in this ratio over all possible inputs, and we are interested in the limit as chromatic number grows to infinity. And this ratio is somehow interested in the behavior of the algorithm for hard inputs. There are other definitions of competitive ratio. This one is sometimes called the asymptotic competitive ratio, and in our paper we focus on this measure of how well an algorithm works. And we saw first fit algorithm in action, and for that algorithm we know that the competitive ratio of that algorithm is between 5 and 8, and this inequality tells us that first fit algorithm is not that bad. So whatever the input, it will use at most 8 times too many colors. And this inequality shows that, well, there are some instances for which first fit can be fooled to use 5 times too many colors. But important thing is that there are such instances for any large chromatic number. So this is important. So this is what we know about first fit algorithm, and one might ask if there are other algorithms and how good they are compared to first fit. Do they have better competitive ratios? And of course, there are other algorithms, and there's a particular one by Kierstead and Trotter, and this algorithm has competitive ratio 3. And Kierstead and Trotter also proved that any online algorithm has a competitive ratio at least 3. So this is quite a nice situation. It tells us that, well, this algorithm here is best possible. It has competitive ratio at most 3, and no other algorithm can do better. I would like to stop here and make a little comment. So in order to prove this statement, you need to construct instances for any large chromatic number, and this construction used to prove this theorem constructs such instances with very long intervals. So dependence of the length of the longest interval in this construction on the chromatic number is exponential, and this is not a nice feature of that construction, and it was one of the starting points for our research, as we were interested whether one can prove a similar statement using construction that uses only shorter intervals. And once you agree that limiting the length of the intervals might be interesting, you can limit them as much as possible, and limit yourself to unit interval case. So you can modify the problem so that all the intervals on input need to have length exactly 1. It's a simpler problem for coloring algorithms, and it's an easy observation that first fit does much better on such inputs. It's an easy proof that first fit uses at most 2 many colors. The competitive ratio of first fit algorithm on such instances is 2. And there is a lower bound by Epstein and Levy, 1.5. And there's a gap between this lower bound and first fit, and it's interesting that we don't know of any algorithm better than first fit. We don't know of an algorithm that has a better competitive ratio. More interesting, even more, we don't know what is the correct algorithm for a case when all the intervals have unit length and the maximum click of the input is at most 4. And this is another starting point for our research. We tried to construct such an algorithm. We failed, but those considerations led us to the next problem. Okay, so at this point I can introduce our main problem. So we modified an online interval coloring problem so that all intervals have length between 1 and sigma, where sigma is a parameter of the problem. And it's quite funny that this problem was not studied before. So there are some papers on such representations, but there are no papers on online coloring of such sets of intervals. So all we get from the previous results is well, the algorithm by Kierstedt and Trotter, it works for any sigma. So we have a free competitive algorithm for all those problems. And the lower bound by Epstein and Levy uses only unit intervals, so it's a lower bound for all our problems for any value of parameter sigma. So this was the starting point for our investigation, and this graph here shows the result of our investigation. So in this graph we have growing parameter sigma here, and here we have the competitive ratio, and this gray area here tells us what are the possible competitive ratios for the best algorithm for any particular sigma. So the algorithm by Kierstedt and Trotter is free competitive. So this is this red line here that tells us that there is a free competitive algorithm for all the sigmas. For sigma equal 1, we have a two competitive algorithm here. This is first fit, and this lower bound 1.5. So this was known before our investigation. And this red line here is our new 1 plus sigma competitive algorithm for sigmas in between 1 and 2. So for sigma 1.5, we get a 2.5 competitive algorithm, and this is our positive contribution. But we also contribute a few lower bounds for these problems. So the first lower bound is 5/3 lower bound for any sigma larger than 1, and this is the best lower bound that we get for values of sigma between 1 and 2. The second lower bound that we provide is 7/4 for sigmas larger than 2. And the third interesting lower bound that we give is a series of lower bounds. For larger and larger sigmas, we get larger and larger lower bounds, and those lower bounds converge to the value 2.5, and we can get as close to this value 2.5 as we can. So say we want to have a lower bound 2.49, then for some sigma large enough we can get it, and for this particular value the sigma is quite large. But the interesting thing for us is that those lower bounds converge to value 2.5 and not to value 3. This still gives us hope that perhaps there are some better algorithms than these three competitive algorithms by Kierstedt and Trotter, and that for smaller sigmas we can get much better algorithms. In this talk, I've decided to talk about the our proofs of lower bounds and not about the coloring algorithm. So for the lower bounds, we've used all the machinery that was already there. So we've adapted proofs of lower bounds by Epstein and Levy and by Kierstetter and Trotter. And especially the second proof needed some work. So there were some technical obstacles that we've had to overcome, and this is some tedious combinatorial work. And we have some new ideas that allowed us to push forward. And in particular, there's a nice feature of our constructions. So all of them have recursive components. So they all start with some strategy, and building on top of that strategy, they construct a new strategy with which is slightly different. Usually it uses a little bit longer intervals, but proves a better bound for competitive ratio. And in order to keep track of the important parameters of strategies, we've designed this notion of alpha, sigma, M schema. So an alpha, sigma, M schema is a set of strategies that for any chromatic number omega and any algorithm I forces any algorithm to use at least alpha omega colors, so it proves a lower bound alpha. But also these strategies have property that they use intervals of length at most sigma, and they span length n, meaning all the presented intervals are inside interval 0m. This allows us to keep track how much space is used for application of the strategy. So there's a very simple 1-1-1 schema. So 1-1-1 schema is just a strategy that for any omega puts omega unit intervals in one place, and you can see that it forces any algorithm to use exactly omega colors, and sigma is 1, and these intervals span only length 1. Okay, and then we have those compositions that build up strategies from easier strategies, and we were able to describe those compositions in terms of how they changed the parameters of the schema. So composition 1, that is based on Epstein-Levy lower bound, has properties that given any alpha, sigma, m schema, it transforms it into a 2 minus 1 over alpha m plus epsilon m plus 1 plus epsilon schema. And sometimes we can apply these compositions many times. So usually we start with this trivial 1-1-1 schema, apply composition 1, we get some schema with other properties, and then sometimes it's desirable to repeat this composition, but now plugging in the schema that we've obtained in the previous step. And this is how we usually obtain our lower bounds. So there are two more compositions that I'm going to skip, and this is the composition 4 that is used to get lower bounds that can get as close to lower bound 2.5 as we want. there's some additional parameter gamma here, which I'm not going to talk about, but again, it's important that this composition, the properties of these compositions are captured by this equation that describes what happens to a schema over the composition. Okay, so these are the bounds that we get. So for example, to get lower bound 2 for competitive ratio, we use composition 4. We need to set this parameter gamma to a particular value and apply the composition starting with its trivial 1-1-1 schema and apply this composition 4 3 times. We get this sigma and this lower bound, and all of our lower bounds have this flavor. Okay, so I want to wrap up this talk with a nice conjecture that we leave in our paper, and the conjecture is that for every finite sigma there is a 2.5 competitive algorithm that covers short intervals. Okay, so that's all. Thank you very much.